Good afternoon, children. Almost evening. Today we are going to do the structure of atom, and under this topic we will be doing at least 4 topics if we can finish. That is the Planck's constant. What is it? Rydbergs constant. What is the Rydbergs constant and how the values are obtained? Then we will be doing the de Broglie relationship, and we will also do Heisenberg's uncertainty principle. So we'll start with the Planck's constant, and to explain the Planck's constant from where it was derived, we have to go to the photoelectric effect. What is a photoelectric effect? That is where we'll begin from. Actually, if you see, the Planck's constant links the amount of energy a photon carries with the frequency of its electromagnetic wave. It is used in Planck's equation, and it is symbolized by a small h, and is actually an inseparable part of many revolutionary formulas. It is used for describing the behavior of particles and waves at an atomic scale. It is used in the formulas for finding out energy, velocity, radius, in Heisenberg's uncertainty principle, in de Broglie's relationship. So Planck's constant is a very important concept that is used in both physics and chemistry when you are studying the atomic structure. So now let us see what is this Planck's constant. And as I said, we will start with the photoelectric effect. For that, I need to use the whiteboard. So let me go to that first. So if we are talking about the Planck's constant, we first need to know what is a photoelectric effect. Now, a photoelectric effect, if you look at it in one glance, is a simple phenomena where in an evacuated vessel, if suitable light is allowed to fall on a metal surface, electrons are emitted. This was first observed by Einstein in 1905. Okay, this was like before the de Broglie's relationship and the Heisenberg's uncertainty principle and all came into the scene. This was in way back in 1905, and it was actually seen by Einstein. Okay. Now, what did he do is he said that in an evacuated vessel, if you are taking a metal surface, you keep a metal surface, and if a suitable light is allowed to fall on the metal surface, electrons are emitted from the metal surface. Now, by a suitable light here, it means that the light should have a minimum frequency, a suitable frequency. If that minimum frequency is possessed by the incident light, then the electron will be ejected. So suppose if this is the metal surface we are talking about, and this is the light which is incident on it, okay, then if it is having the minimum frequency, which is also called as the threshold frequency, then an electron from the surface is ejected. Now, 2 things will happen here. First, when I'm talking about the incident light, it should possess a minimum frequency, which is called as the threshold frequency. If the threshold frequency is not there, however much you increase the intensity of the light, electrons will not be ejected. So for the electrons to be ejected, the frequency is a must. That minimum frequency has to be met with. If the incident light has the threshold frequency or has a frequency greater than the threshold frequency, then the electron is emitted from the metal surface, and that extra frequency, more than the threshold frequency, is used by the electrons in gaining its kinetic energy. It is imparted as the kinetic energy to the electron. Here, if you increase the intensity of the light, more number of electrons will be ejected. So 2 things. Number 1, number of electrons that are ejected, they will depend on the intensity of the light only if the minimum frequency is met with. All right. If for a particular metal, a particular minimum frequency is required, and only if that frequency is there, will the electrons be emitted. However, number of electrons that will be emitted or which will come out will depend upon the intensity of the light. As I said, now, suppose if you are talking about this photoelectric effect, then usually a radiation in the ultraviolet region, and in some cases in the visible region also, they will produce such effect. The velocity of the ejected electron, which is which is also imparting the kinetic energy, can be measured by the external electric field with a potential V, where a V is the potential required to just stop the photoelectric current. Okay, so let us go to the derivation part that we were talking about here. There are two things we were discussing. Number one, that the electron will be ejected. Electron ejects, all right, only when the threshold frequency is met with. That is, the energy is equal to, E is equal to h nu. All right, nu naught. Nu naught is the threshold frequency which is required. However, the kinetic energy that is possessed, the kinetic energy of the electron that is possessed by the electron should equal to half mv square. Okay, this should equal to half mv square, where v is the velocity. Okay, now we said that the kinetic energy that is imparted to the ejected electron will actually equal to h nu. This is the frequency, that is h into nu. This nu is the frequency which is greater than the threshold frequency. So this I can subtract from h nu, I can subtract from h nu, h nu naught I can subtract from h nu. This one will equal to its kinetic energy, or I can write this as h into nu minus nu naught. Now this is called as the work function. This is also referred to as work function. That is the amount of energy that is required to pull out an electron from the surface of the metal. But again here, this will need, or the minimum requirement is that minimum frequency that will be required. Now, if I'm talking about this kinetic energy that is imparted, higher will be the frequency of the incident light, greater will be its kinetic energy, and vice versa. Now, if the values of the work function and the ionization potential are compared, why I am comparing it to the ionization potential here is because ionization potential is also the amount of energy required to pull out a most loosely bound electron from its isolated gaseous state. All right, so there, from an isolated gaseous atom, an electron is to be pulled out. Here we are going to, what we are discussing is that an electron is pulled out from the surface. All right, that is, you can explain it on the basis of the Planck's concept of quantization of energy. It should be understood that emission and absorption of the radiant energy is always quantized. And each quantum, that is a particle nature we are talking about, each quantum is traveling with the velocity of light, and it will give up its entire energy to the electron on the surface of the metal, to the electron on the surface of the metal. A portion of this energy, which is equal to the work function as I just said, all right, is utilized in emitting the electron or in ejecting the electron free from the surface, that is free from all the attractions that are there. And the balanced energy is then converted into the kinetic energy. That is what we just did here. Now, if you compare the values of the work function and the values of the ionization potential, then you will see that the work function is less compared to the amount of energy required in removing an electron from a gaseous atom. For example, if you take the case of a sodium metal surface, you will find that if the threshold wavelength that is used, if it is 5,000 angstroms, okay, then the work function in this case is only 2.5, whereas electron volts, whereas in the case of ionization potential, it is as good as 5.12 electron volt. All right, so you can see, understand that in the case of the gaseous atom, it is the amount of energy required is more, that is the ionization potential is more. Here I have just done a little comparison of the work function and the ionization potential. Remember, they are two different phenomena. What I'm talking about in the photoelectric effect is the ejection of the electrons based on the amount of the energy which should possess a minimum threshold frequency. That is what we are talking about in the Planck's constant. Now, from this, the kinetic energy could be measured of the ejected electron can be measured, and V minus the frequency values can be obtained, from which the value of H can also be obtained. And when the value of H is obtained, obviously we can further continue with the its usage in the other formulas. And the value for the Planck's constant is given as 6.626, all right, into 10 to the power minus 34 joules and joules seconds. This is the value that is used. Okay. So further on, wherever we will use the value of H accordingly to the units, we will do that also. Okay. Now coming to the next constant that we are talking about is the Rydberg's constant. Now you must know that the wavelength and frequency of light are closely related. Higher the frequency, shorter is the wavelength. This is because all the light move through a vacuum with the same speed, and the number of crests that are passing through a point in 1 second, that depends on the wavelength. All right, that is, the wavelength is inversely related to the frequency. The greater is the frequency, less will be the wavelength. All right, and energy of a wave is directly proportional to its frequency, but is inversely proportional to its wavelength. All right, so keeping this in mind, we will proceed with the Rydberg's constant. Now, if we have to go to the Rydberg's constant, we need to go to the spectrum. And in the spectrum, we said, or in the hydrogen spectrum, or in the atomic orbitals, you can go to. We know that the electrons make transitions from higher energy levels to lower energy levels. And if you look at the hydrogen spectrum, it has the Lymer series, the Balmer series, Paschen, Brackett, Efund, and the Humphrey series. Now, these series have a definite you can say description of themselves. Like a Lyman series is a series obtained when an electron is jumping from any higher shell to n equal to 1. All right, so it can take a jump from n equal to 2, it can take a jump from n equal to 3, n equal to 4, from wherever it is jumping and coming to. If it is taking the transition from any of the higher energy levels and coming to n equal to 1, then you say that it falls in the Lyman series. Similarly, if it is jumping and coming from any other higher level to n equal to 2. All right, so let this n equal to 1 be here. When it is taking a transition from the higher energy levels and reaching n equal to 2 level, then the transitions are called as, in the case of Balmer series. So this way you have all the series which we have already discussed in the spectrum, hydrogen spectrum. Okay, now to understand the Rydberg's constant or the Rydberg's formula, let us first know that the Rydberg's formula determines the lambda of a light emitted by an electron moving between energy levels in an atom, usually from a higher to a lower level, and a photon is emitted. All right, that is, a photon is emitted. Now, if I have to derive the value of the Rydberg's constant, all right, this is Rydberg's constant. Rydberg's constant, if I'm going to this, all right, then remember, we are trying to, what did we say just now, that Rydberg's constant or formula determines the lambda of the light, that is the wavelength of a light emitted by an electron, which is moving between the energy levels within an atom. All right, and usually we will take the case of an electron which is moving from a higher level to a lower level, that is, a photon is emitted. So let us take this case where an electron is, in the second shell, that is n equal to 2, is jumping to the energy possessed by n equal to 1. Why I am writing E here is, we are going to use the energy values, that is why. So E, it is in the second shell and it is going to jump and come to the first shell. And obviously energy is going to be emitted. The emitted energy can be given as, the emitted energy, that is E2 minus E1, will be given as, you will have to use the energy formula that we have done already, that is minus 2 pi square, okay, m E4, all right, divided by n square h square. Okay, and if you are using the permittivity in free space, then of course you will get a 1 by 4 pi epsilon naught will also occur. Now this, you keep this here, then you put a minus sign, and again within the minus sign you will have 2 pi square, okay, m e4, okay. Here this is n is 2, here this one will be n is 1 square h square. Okay, so this is within. Why I have kept it within the brackets is because in this case you will see that the minus sign has to be understood correctly. Now in this case what I can do is, now I can write this as taking this on the front side, because this minus will become plus. I can write this as 2 pi square m e4, okay, divided by n1 square h square. That is, h stands for the Planck's constant. Remember, Rydberg's constant is given by a capital R and h is given as the Planck's constant. Now this minus, I will use this one, that is 2 pi square m e4, okay, divided by, it's going to be n2 square. N2 stands for the second shell, and of course it's going to be h square. So now what we will do is, we will take out the common terms. Now if you are using the permittivity in free space, even 1 by 4 pi epsilon naught square will also occur in the formula that we will add towards the end. Okay, so in this case I can take out the common, that is 2 pi square m e4, okay, this can be taken out as common, and h square can be taken out as common because that's the Planck's constant, and this I can write within brackets as n1 square minus 1 by n2 square. All right, so you can see within the brackets is indicating the transition of the electron from n equal to 2, it is coming to n equal to 1. All right, this is the final place of rest where the electron will come, and this is where the transition begins from. So n2 is given. Now in the above case, I can now also write this as h nu. You see, because it is the change in energy, if this is delta E, then this I can write as same as writing delta E will equal to h nu. Okay, this nu hasn't come out properly. Wait, h nu. All right, now this h nu that is coming out here, this is also equal to h, okay, c by lambda. All right, this is equal to 2 pi square m e4 divided by h square, okay, and then this is 1 by n1 square minus this is n1, 1 by n2 square. Okay, now let's go to the next page, because in the next page I can't write below this. So in this case I can also write that as h c by lambda was there. So I want to use the find out the wavelength. All right, so I can write this as 1 by lambda is equal to, I can write it like this as 2 pi square m, okay, e4 divided by h was already there. Remember, h square was already there. So another h from here is coming. So this one will become h cube, and c I am taking here. So it becomes h cube c. That is the velocity of light. And I can include the value of the permittivity in free space here also. And I can write this as 1 by 4 pi epsilon naught square. This I can use it right from the beginning, or I can introduce it here. Then after this, within brackets, it will be 1 by n1 square minus 1 by n2 square. Okay. Now, once this is done, this can also stand for the wave number. So I can also write this as, a bar over the new sign, which is the wave number, which is reciprocal of 1 by, which is reciprocal of lambda, that is 1 by lambda here. Now, if you substitute the value of all this, if the values of all this are substituted, then the value turns out to be equal to, that is 2 into 3.14. If you want, I can write it. 3.14 whole square, I can make it into mass is going to be, if I'm taking it in terms of grams, then it's going to be 9.109 into 10 to the power minus 28. Okay, this is grams. In that case, the charge that I will take will be 4.8 into 10 to the power minus 10 ESU. This is the charges in terms of ESU. This one will be raised to the power 4. And of course, you'll have the permittivity value. And this Planck's constant is 6.626 into 10 to the power minus 34. If you substitute the units also, then it will be easier for you to get the value. Since we are doing it in the CGS system, this one will be minus 27 and not that. So this one is going to become Q. And of course, the velocity of light is taken as 3 into 10 to the power 10 centimeters. Okay, or you can leave out the units here, and overall, when you calculate this, the value turns out for this. And of course, it is only this part that I am showing here. Okay, then after this, you will get this value as 109,679 centimeters inverse. This is the value of the Rydbergs constant. Now you see, this is the value of the Rydbergs constant for hydrogen atom. Why? Because hydrogen atom, we have not used the value of Z. If you go right in the beginning, you will find that if Z was to be included, that is, if the atomic number, if it was not a hydrogen atom and it had an atomic number greater than 1, then a Z square would have occurred here, all right, in the formula. So if the Z square would have occurred, then obviously for multi-electron atoms, that Z square and the permittivity in free space values are also included in the calculations. But what we are learning here in standard 11 is the Rydbergs constant for hydrogen atom, that is when the atomic number is 1 and the electron is 1 and the values are substituted accordingly. So this is what is the Rydbergs constant all about. All right. Now for multi-electron atom, what will happen is that obviously the values will have to be used as the square of its atomic numbers. All right. Now related to this, what are the other things that you are supposed to know? Okay, what kind of questions you can get from this? To understand that, remember, let us say you get a question like, which one is the shortest wavelength in the Lyman series? All right, in the Lyman series, which one will have the shortest wavelength? Which one will have the longest wavelength? So remember that the shortest wavelength in the Lyman series, all right, is given as, that is 1 by lambda, if I'm talking about, is given as RH. All right, the shortest wavelength will be when the transition is from, this is square, all right, minus 1 by infinity square. Okay, that means infinity. Okay, this is there for the shortest wavelength. You see, the shorter is the wavelength, the higher will be the frequency. All right, higher is the frequency, more will be the energy. Similarly, this is for the shortest wavelength. For longest wavelength in the Lyman series, the longest lambda for the Lyman series, okay, it's not right, Lyman series, all right, will be from where? If that is what you have to understand, then 1 by lambda, in the case of a hydrogen atom, if we are considering, remember, it is going to be 1 by square, all right, minus 1 by 2 square. That is the second shell. So you can understand that in this case, 1 by lambda is actually equal to 3/4 RH. Right, that is Rydberg's constant is used here. Okay, or you can say, or we can say that lambda is equal to 4 by 3 RH. That is the Rydberg's constant. And if you substitute the values for this, you will get this as 4 divided by 3 into 1096 This is the value we just got, right? 6, 7, 9. Then this turns out to be equal to 1215 point, I think it will be 9 nanometer, and accordingly you can find out the values to understand this. So what I'm trying to tell you here is that the shorter wavelength, that is when you are having a shorter wavelength, the frequency is higher and it corresponds to greater energy, which is quite understood that if an electron is away from the nucleus, it is at a higher energy level. And when it is having a longer wavelength, then obviously it is associated with less energy. And you can see that in this case, it is jumping from the second shell and coming to the first shell. So this was about the Rydbergs constant that you have to learn. Now, what kind of questions you will get here is that in the exams or in the question paper, they may tell you that a certain transition is occurring in the Balmer series. Now, when it says Balmer series, it is understood that you automatically know the value of this one. That if it is the Balmer series, n will equal to 2. If it is the Lyman series, this n will equal to 1. All right. So if it is the Pastel series, bracket series, you're supposed to know the value of n. So if you have done the spectrum properly, then you will not have a problem in selecting this. Usually the numericals are based on the Balmer series because it falls under the visible region, and questions are often based on that. And if the transition is in the Balmer series, you know that the value of this n, I'm talking about this n here, this is going to have a value of 2. And of course, the transitions will always be from n equal to 3 and above. That means the value here will always be 3 and above. That is third shell, fourth shell, and so on. So if the Rydbergs constant value is known, and if the transition is taking place in the Balmer series from the fourth shell or from the fifth shell, then you can very easily find out the lambda, you can find out the wave number, and of course you can also find out the energy. If you have to find out the energy that is emitted, obviously in this case, then you will have to use this formula. All right, then that h cube c will not occur, because if you are finding out energy, that is this these values, then you see you have to use it as h nu here, and therefore then accordingly you can find out the energy that is emitted by the electron which is undergoing or which is moving between the energy levels in an atom. Okay, children. So this was related to Rydberg's constant. Maybe in the next class we will do the de Broglie's relation in the next video, the de Broglie's relationship and Heisenberg's uncertainty principle. I hope this is okay with you. I'll just go show you all the slides one more time. So this was about photoelectric effect. Then this is okay. This was about photoelectric effect. Then this is about the Rydberg's constant that we were doing. Of course, the first one was related to the Planck's constant, where the value of h can be calculated. And then this is the Rydberg's constant, and of course, how you find out the value. And this is the last one is related to the short wavelengths and the energies associated, longer wavelengths and the energies associated with that. So I hope this is okay with you. In case if you have any doubts, you can always call up and find out, clear your doubts, So I hope this is okay with all of you. Now coming to the next topic that we will do in the next video. So this is enough for today, I think. All right, children. Thank you for connecting.